Hi, everyone. Thank you for attending my talk. I will be speaking about how to teach students their first quantum algorithm at an undergraduate level. The overview of my talk is that I think that the Deutsch Jozsa algorithm, which is often taught as the first algorithm in undergraduate courses, solves a very artificial problem that is very unmotivating, and it's also unclear how this algorithm works in the first place. So I am proposing in this work a different first problem and algorithm to present to students, and I think it's a lot more intuitive. Could I ask who has studied or taught the Deutsch Jozsa algorithm before? Okay. Cool. So I'll begin by talking about how it's taught right now, then presenting my approach, and ending with a discussion. The Deutsch Jozsa problem is really artificial. The first problem you might study in a classical algorithms course might be something like searching a list, navigating a graph, sorting a list, and so on. Things that really are used every day. But this is what gets presented in most quantum computing courses. Given a function, is this function constant, which means it outputs the same output on every input? Or is it balanced, which means it outputs 0 on half of the inputs and 1 on the other half of the inputs? This might be relevant to something in cryptography, but it's certainly not a good candidate, in my opinion, as a first problem. Um, and the way it's solved is even more disappointing. The Deutsch Jozsa algorithm is a circuit that looks like this. You've got an oracle, and you surround it with a lot of Hadamard gates. And this is really from some quantum algorithm notes. People will just say things like, well, if you don't know what to do in a quantum algorithm, it's always good to just try putting Hadamards everywhere and seeing what happens. And I think the intuition that's typically tried to be communicated is it's something like the double slit experiment where you've got some interference pattern going on, and we don't quite know why, but the interference pattern works out perfectly if you set it up like this. This is what you might find in a textbook, 3 pages of calculations to prove that that interference pattern actually does what it is supposed to. And this is not, in my view, an explanation. It is merely a calculation and a lot of finicky details of how to move things around on the piece of paper. Here's where I would start. The decision search problem. It's like a search problem, but you're just trying to see, is there a search result or not? So you've got 2 possibilities for this function. It's either giving you 0 everywhere, that means there are no search results, or it's giving you a 1 at least somewhere. And the goal of the algorithm is to determine which case you're in. So if you were a classical algorithm trying to solve the decision search problem, you could try randomly sampling the function and seeing what outputs you get. And the moment you found a 1, you would know that, okay, this is a yes instance. Sorry, I'll just go back to the previous slide. You try a bunch of different inputs, and the moment you see a 1, you say, this is a yes instance. And if you've seen everything and you got zeros everywhere, then it's a no instance. So now I focus on decision search, but with a single evaluation. Suppose you're limited, you only get to test your function 1 time. Then, well, what can you do? You randomly sample, and if you get a 0, you say this is a no instance. But if you got lucky and you got one of the 1s, you say it's a yes instance. Okay, so it's a very simple search, decision search, and only restricted to a single query. Now, if we use the quantity R to determine the ratio of outputs that are 1, so for example, if the function had output 1 on every input, then R would be 1. Otherwise, if it was a balanced function, then R would be 0.5. If we use that quantity R, then the probability of this algorithm failing is 1 minus R. That's the probability of you picking one of the zeros. So now I've set up the problem on which I would rather start, and I've set up a simple classical algorithm for this problem. Let me tell you what the quantum algorithm looks like. It's a lot nicer than the Deutsch Jozsa algorithm. Before I can talk about it, I need to introduce the subroutine called quantum state equality. And I would say that quantum state equality can be thought of as, well, we need some sort of equal sign operation in our quantum programming language. What would that look like? So here's what that might look like. Suppose I handed you in a quantum computer a quantum state psi, and I told you about a quantum state phi. So I described a quantum state phi in its full classical description, but psi I gave to you already loaded up in a quantum computer. And your task was to determine, are these two states the same? Okay, so it's an equality check between two quantum states, one given to you, one described. There's a simple quantum circuit to perform this task. It basically involves unpreparing the state. So if they were the same state, unpreparing the state will get you back to the zero state. And if they were different states, it'll get you to some other state. And to skip the details for those who might not be following all the technical points, this equality check will succeed deterministically if the states are equal. So if the states are equal, the equality check will always tell you that they're equal. But if the states are different, then it might fail because quantum measurements have this randomness. And the probability with which it fails is this quantity determining, it depends on the inner product of the two states. Okay, so we have some sort of notion of equality between quantum states. I think it's a good thing to set up. I think many courses have the requisite concepts like measuring on an orthonormal basis, Born's rule, and these concepts will allow you to set up this notion of a quantum state equality as the first concept. Once you have this concept of equality of quantum states, you can now describe the decision search quantum algorithm. If you have one evaluation to do decision search, how do you do it? So the first thing to know, which this will be familiar to those who have studied the thing, studied Deutsch Jozsa or any other quantum algorithms, but a common trick is you use the oracle, you use the single access, the single quantum access to the function you have to prepare the state which encodes the function as a whole. So whereas the classical algorithm was only able to sample the function at one place, the quantum algorithm builds this like function state that in some sense represents the whole function. It's a superposition of all the pairs in the function. And what's cool about this is that if this function was a no instance, then we know exactly what the state would be. It would be, all the pairs would have a zero in the second component. So what we'll do is we use our one query to prepare a representation of the function. And we know what we want, we know what the function would be if we know what the state would be if the function was a no instance. Okay, so I'll say that all again. We have just set up this like equality operation, and we're going to use it by first using the oracle to prepare a representation of our function, and then checking if that representation of the function is equals to the constant zero function. Okay, and let me just show you what that would look like as a computer program. It would be a more intuitive computer program, I think, than that quantum circuit with the Hadamards, because it just says, look, build your representation of this function. And if that state that you get is equals to this reference state of constant zero, then output no, this is a no instance. Otherwise, output yes. This algorithm has a better performance than the classical algorithm. Remember that the classical algorithm was randomly sampling one value, and so it had a failure probability of 1 minus RF. As I had this at the bottom of the previous slide, here you can get 1 minus RF squared. That square comes in because of Born's rule, the measurement statistics of quantum states has the square. And again, that will be familiar to the more technical audience. So now what I want to say about this algorithm is so far, what we've gotten to is a different problem and a very neat algorithm, but you might think, is this allowed? Like you've just talked about something completely different. One thing I'll say is this is a much simpler problem. It gives you a cleaner speed up of like, this is basically doing what in two queries a classical algorithm would do. It's doing in one query. That's how the square can be interpreted. But I will now show you how this is actually just related to the Deutsch Jozsa problem. And the way I'm going to do that is I'm going to point out that in this very simple algorithm, we can change how we choose to encode the function in the first place. So this is a particular choice of encoding of the function, and we can sort of see it as swapping out the data structure. We use a different encoding of the function f, and then we're able to get different performances of the algorithm. So here are three encodings. These are also commonly used in quantum machine learning. Bit encoding, sign encoding, and angle encoding. It just changes where you put that information about the function. Do you put it in another register? Do you put it in the sign? Or do you put it in a rotated qubit? So In this slide, I've plotted all the different performances of those different data structures and also the classical algorithm. And what you see, the straight line is the classical algorithm. That's that function 1 minus r. If the ratio of inputs is r, then the failure probability is 1 minus r. That's the line. In this graph, down is better because that's lower failure probability. And the yellow line, which is always below the blue line, is that first quantum algorithm that we saw. So that's how you can set up a quantum algorithm and say, look, this achieves an advantage in all cases. Now, to get to the Deutsch Jozsa problem, we use the sign encoding, which is sometimes lower than the blue line, but sometimes above. And that's kind of an interesting thing. To the side of the audience that isn't really following the technical details, I'm sorry, but to those who have studied the Deutsch Jozsa problem, I speak to you now. It's really cool that that one point there is the story we get told. That's the Deutsch Jozsa problem where you're promised constant versus balanced, and you get a zero failure probability. And people talk about how cool it is that the Deutsch Jozsa problem is deterministic and so on. But really, it's the tip of the iceberg of a broader story. And I think this broader story, which is in this graph, merits being told. So that's the end of my presentation. Sorry that I had to split the audience a little bit. I had to speak a bit more technically and some parts. But now to come back to everything, what's the big upshot of all of this presentation? Search is a more natural first problem to introduce than this constant versus balance problem. So I think students entering a quantum computing course will feel more at home. To speak in terms of what the previous speaker said, this is a more familiar concept. If you're a computer scientist, you haven't really, why would you want to care about constant versus balance? Like, give me a search problem or a graph problem or something I've seen before. Give me something analogous to what I've seen before. I also think these concepts of quantum state equality and the encodings of functions, the different encodings of a function, these are reusable concepts. And I'm working with these concepts in my research in quantum data structures. So I think setting them up early is good because then you give students algorithmic tools they can actually use in designing other algorithms. And you can set example problems and homework problems where you reuse these concepts. If you're fixed with this rigid interference pattern, there's not much else you can do. Now, I actually want to point out a mistake in like Nielsen and Chuang, where in that book, the great textbook we all always celebrate, it mischaracterizes the Deutsch Jozsa algorithm as relying on the Hadamard transform. And I think this work has shown actually you don't need the Hadamard transform. You just need to be able to prepare and unprepare the uniform superposition state. And there are many oracles that do that. There are many unitaries that do that. So I think our communal lack of understanding of the Deutsch Jozsa problem extended till the frontier. I don't think anyone knew this about the Deutsch Jozsa problem. And I think the key insight from all of this work for me has been that the data structure matters. The story you tell about what is your quantum computer representing? What is the interpretation of that data? And how are you actually modifying that data? How are you then getting data out? How are you then extracting information out of it? These are the questions you ask in the field of data structures in computer science. And I think that perspective and using it in quantum algorithms has really helped me shed light on existing quantum algorithms and also design new quantum algorithms. So I hope this work will lead to more presentations in the future at this venue and others about new interpretations of quantum algorithms in terms of more familiar concepts to different communities. And I hope that will catalyze the development of new quantum algorithms because we really need that. We don't have as many applications of quantum computers as we wish we would. So I hope to see more discussions, not just of teaching of quantum algorithms to beginners, but also to slightly more intermediate and advanced students. Thank you so much.
We have time for a question or two.
Thank you for great talk. And my question is, I feel that your new algorithm is can explain the notion of the quantum parallelisms, right? But actually, the important concept of the quantum algorithms is like amplitude amplification. But maybe I guess that your current algorithms cannot explain about that. So how do you have any idea about how can we explain the another concept?
Yeah, thank you. That's a good question. So one thing I'll point out is the Hadamard transform is essential in the case of amplitude amplification, and or transforms like that. And I think that's the confusion that people were led to in this sort of thing. So splitting that apart is actually a strength of the work, that this doesn't talk anything about Grover search or amplitude amplification. But based on this work, I am preparing another paper, which, because of this perspective, allows you to see how you would discover Grover's algorithm for yourself. If, again, I want to stick my neck out today and like take the risk and say, I don't want quantum algorithms where I don't understand how you thought of them. Like, I want quantum algorithms where I could have thought of that myself too, and your idea is cool. And I don't want to just do some calculations to be sure that your algorithm works. I want to be able to come up with them. And this perspective of inner products allows me to set up an axiomatic way of deriving Grover's algorithm. So that's a work that I'm developing at the moment, and that would answer your question of how you get to amplitude amplification. Actually, this perspective of the inner product being something you want to reduce, you can think of amplitude amplification as taking steps to make the inner product smaller and smaller and smaller. So you need to introduce a new primitive on top of this idea, but if you introduce that new primitive, then you get to amplitude amplification.
Oh, that's cool. Thank you.
Do you feel that this is most suitable for a particular audience, or is it good generally?
My test. Oh, that's very different. Yeah, I think this is good for undergraduate audiences in general. I think that at first I used to talk about this work as being good for computer scientists, and then physicists got offended because they liked it, and so they said, well, why can't it be for us? So that would be my perspective. Yeah.
Well, let's thank our speaker and invite our next speaker up.